in the last portion of the previous lecture, we talked about the need of the solid state joining. Okay, and one of the major purposes which is served by the solid state joining is that it doesn't contribute, like SSJ processes do not contribute towards the weight gain. See, this is one of the and then other factors like all of you will agree, these are mostly the low heat input process. Although in SSJ also we have low heat input and high heat input processes. So in low heat input processes, say temperature rise may not be 150 degrees centigrade, and in the high heat input process, although base metals still remain in the solid state, but the temperature rise may be well above the recrystallization temperature. So those you may call as a high heat input process. So, but as compared to the fusion welding, the heat input is low. And the another good part related with this solid state joining is that the thermal damage to the base metal, or parent metals it's very negligible, or it's very less, because many advanced metals, can you see the screen now? Are you able to see what I'm writing? Yeah, okay. So many advanced metals which have been developed, they are thermal sensitive, they get affected metallurgically, so the property alteration deteriorates their performance. Similarly, the metal matrix composites, MMCs, or fiber metal laminates, which are developed for high-end applications, these are very badly affected, especially when we have to join using the high heat input process. I'll give you one simple example here. Say the most common the metal matrix composite, like say they are most of the metal matrix composites, you can understand like this, that they are reinforced with this some kind of the reinforcing agents, okay, in the metal matrix. And most of the time these are either hard or they are soft also to provide a specific role like lubrication. So the aluminum graphite composite is one of the typical example where soft reinforcing agent is used. Otherwise mostly these are hard one, like it may be in form of boron carbide or tungsten carbide or titanium carbide. So these are mostly the hard particles which are reinforced to enhance the properties or hardness and strength of the completely soft and tough metals, mostly say aluminum or the titanium. So what is happening, like when we use the high heat input process like in fusion welding, so we have to bring all these to the molten state, and when it is done, you will find that all these get thermally damaged. All reinforcing agent, they will get thermally damaged very badly. They will get decomposed, brought to the molten state, they will be losing their identities. Similarly, the regions which are very close to the fusion zone or the in heat affected zone, which are the zones which are subjected to very high temperature, they are also the metal and reinforcing agent characteristics are adversely affected, okay. And one of the most common problem related with this is the wetting and poor bonding between the reinforcing agent and the metal matrix. So this leads to the lot of pores and the discontinuities in the joint, okay. That's why apart from thermal damage, this also promotes like fusion joining also promotes the discontinuities in the metal matrix or the fiber metal laminates or many other kind of the dispersion hardened the composite materials, so they are not considered to be good. That's why the solid state joining may be preferable for joining of such kind of the metal systems. Lastly, I also talked a little bit about the one interesting word was there, that was like say the damage tolerance. Damage tolerance, and about this probably I talked little bit. Like say the joints cannot be developed without discontinuities in general. This is the common understanding. Whenever there is a kind of the joining, you'll always find the discontinuities of a small or large size. Okay, so there are two aspects. Whatever the discontinuity is present, and it is there with most of the real joints and real metal systems, so means we have to live with these discontinuities in case of the joining or in case of the real metals. Now, what kind of the discontinuity, what size of the discontinuity that can be tolerated has to be identified, and that to a great extent depends on the criticality of the application. Criticality of application, like if there is a discontinuity for a joint which is subjected to the static loading, okay, simple tensile or compressive load, probably the discontinuities may not be that damaging. Why? Because there is enough time for localized yielding in vicinity of the discontinuity and reduce its severity. Okay, but that is not the case in case of the high strain rate loading conditions like in fatigue or impact. In those cases, we will see the discontinuities very adversely affect the performance. Depending upon the criticality of the application, kind of the loading, the relative importance of the discontinuities vary, or it will be different. So the discontinuities are more crucial in case of the fatigue and impact conditions as compared to the static load conditions. Likewise, in a typical weld joint where stress concentration or inherent stress concentration is less, so the discontinuities may not be that big problem as compared to the case where stress ratios are very high. Apart from this, the role of or significance of the discontinuity is also affected by the yield strength of the metal. In general, the metals of the high yield strength show greater sensitivity towards the discontinuities as compared to the low yield strength, and the reason behind this is very simple. High yield strength metals, they do not deform easily in vicinity of the discontinuity, so they don't reduce the stress concentration effect being offered by the discontinuities. On the other hand, if the metal is of the low yield strength and good ductility, localized yielding will easily be taking place, and that in turn will be reducing the stress concentration being caused by the discontinuities, and so their severity will be reduced. So a high yield strength, high sigma y, greater will be the issues related with the discontinuities. Okay, this is one thing. So how to quantify that which one is good, which one is bad, how much is to be how much can be tolerated? So that those things to a great extent depends on the metal fracture toughness. This is a new word, fracture toughness. Okay, fracture toughness. and this there are number of parameters, and one of the most common parameter which is used to quantify the fracture toughness, like say stress intensity factor is 1, okay, CTOD, crack tip opening displacement, is the second, and the J integral is the another parameter. So the stress intensity factor, typically this is the most common one which is used in for the design purposes. It is represented by the letter K, okay, since mostly we things are designed based on the tensile stress conditions, like for the tensile mode of the fracture, so we show it like 1, K1. When it is shown by the K2, means this is for the mode 2, the stress intensity factor for mode 2, which is for the shear loading. I'll talk little later like what are these different modes. And similarly there is a mode 3 also, which is also for shear but in the different way, okay. Mode 1 is for the tensile stress conditions, that's like it is called a crack opening mode. So stress intensity, so fracture toughness, most common parameter is the K1, okay. This is the stress intensity factor for a metal, but when we have to use this for the design purpose, like say a particular metal will show its critical stress intensity factor. So this is one of the parameters of the fracture toughness, which is represented by K1C, and this is basically metal property, okay. This is just like yield strength, used for the design purposes. Similarly the K1C is also quantified. What it shows, like there is a crack in a metal, so what we do, we apply the tensile load and try to see at what stress level, under what loading conditions this crack starts to grow, okay. So that resistance to crack growth is quantified in terms of this stress to be applied using the external tensile loading system. So this is a typical called compact tension CT specimen test, okay, for quantifying the K1C. So let us not get into the many details. The K1C is one of the metal property which is a critical stress intensity factor used for the design purposes, and what it shows, it is simply represented under the simplified conditions. Say this is one, you can say the proportionality factor, you can say Y into sigma by C, okay. The C is the, you can say, the defect or discontinuity size, it depends where it is located, and the sigma is the applied stress, and this is mostly, you can say, it is taken one when it is of the large width, okay. So further simplification, sigma pi C is the one which represents to the stress intensity factor. And if we know, since this is a material property and we know that for a given metal is 200 and the material is being subjected to the stress of 100 MPa, then what will be the critical size of the defect? That is what we can easily calculate, okay. So for a metal having the stress intensity factor 200 MPa, applied stress this is unit for this is MPa raised to the power 1/2. This is the unit of the fracture toughness critical stress intensity factor unit. Okay, so this is 200 say for a metal which is very high for the metals like austenitic, stainless steel, or the super alloys having very good fracture toughness. Otherwise metals like aluminium or the magnesium, they may be having 10 or 15 units of the fracture toughness. Okay, when it is subjected to the 150 MPa, then you can calculate easily what will be the size of the defect. Now how do we calculate? See, it depends on the where the defect is located. It is internal or external. For the defect which is external, means that located at the surface, that C is taken as equal to the defect size, and C by 2 when the defect is located inside, then the C is half of the total length of the discontinuity. So the length of the discontinuity when it is present at the surface is equal to the C, and the length is half of the length of the discontinuity when it is located inside. So there are the different way of calculation, but the thing here is which I want to explain, the damage tolerance. Like for a metal it is 200 and you have got, say, you calculate and you will get the C value. So that will be indicating that this is the size of the defect, the above which fracture will take place, and below that the fracture will, the discontinuity will be tolerating the fracture. Okay, so if the metals, the fracture toughness is 300 or 50 for a given applied stress, so for 150 and for the 300, the tolerable defect sizes will be different. The tolerable defect size for 300 fracture toughness, for metal having 300 units of fracture toughness, that will be much larger as compared to the metal having the fracture toughness of 100 MPa, or those which are having like say 10 to 15 MPa raised to the power m, those metals having the fracture toughness very low. So obviously their capability to tolerate the discontinuities will be very negligible. Okay, so we need to be more careful while developing and designing the joints. Okay, so this was all though just to tell the significance and importance of the defect tolerance or damage tolerance. I talked at length about this. So say for one metal, say one steel having the fracture toughness of 300 MPa, it is raised to the power 1 by 2, and say aluminum having just say 30 MPa power 1 by 2. Okay, so now for a given applied stress, now there are two different scenarios. For a given applied stress, say 150 MPa, the tolerable size of the defect will be different in tenfold. See, very small tolerable crack size for aluminum and very large, like 10 times greater tolerable crack size or defect size will be there for the steel. Okay, now coming to the joining. Okay, so when we perform welding very poorly, like say poorly means inappropriate welding conditions leading to joining, or welding conditions leading to the compromise with the base metal properties. Okay, when it is happening means certainly they will be compromising with these fracture toughness kind of things, not just yield strength. I'll tell you one more thing, the fracture toughness and the simple toughness, these almost go together, but the significance is different. Simple toughness indicates the energy absorbed under the high rate of strain loading during the impact conditions, while this indicates the resistance to the crack growth, okay, which is quantified in different ways. One I have already talked, like stress intensity factor. There can be other energy based criteria also, but the fracture toughness is used to indicate the resistance to the crack growth. Okay, so since both are going hand in hand together, so how do we how can we relate the toughness with the mechanical properties, like say the strength, yield strength and the ductility? These are two which will be affecting the toughness. How? This is the simple your stress strain diagram, right? All of you are familiar with this. So area under this diagram is used to indicate the energy required to cause the fracture, isn't it, under the tensile loading. And this area will depend upon what? So this indicates the energy requirement. Okay, now this area is function of what? There can be different scenarios. In one case it goes in like this. Okay, so area, in this case area under the curve is very limited. You means tough, say this is the case of the say cast iron, strength is high but the ductility is very limited, deformation is limited. Okay, on the other hand the metal is of the low yield strength, but and higher elongation, so in this case area is little bigger. If you take third case where strength is also good, ductility is also good, so if you see this scenario here, not just a strength but long elongation, significant elongation prior to the fracture. So in this case the energy absorbed will be maximum, in this case it will be minimum, and here it will be moderate. Okay, so this may be the case of your austenitic stainless steel, this may be case of cast iron, and for other steels like medium carbon steel, this may be the case for the medium carbon steel. So if you see here, it is the strength or yield strength and the tensile strength and the percentage elongation, both are contributing towards the toughness. Since the toughness and fracture toughness both are going hand in hand, so greater the toughness, greater the yield strength, greater the ductility, means higher will be the fracture toughness also. So those metals which show good ductility in combination with the good yield strength, they certainly show the high fracture toughness. No, but when you perform the welding inappropriately, joining inappropriately, using poor joining conditions, then both yield strength and ductility, percentage elongation, or both are compromised. And once, if either both or any of these two, if either of the two, if they are compromised, means your fracture toughness is compromised. And if that is happening, then certainly your tolerance to the discontinuity is compromised. Means now earlier you were able to, your joint was able to tolerate say 8 mm. Now your joint can tolerate just 4 mm or 3 mm size discontinuity for a given loading conditions, and beyond that it suddenly goes in catastrophic manner. So the things fail. Okay. So this is one aspect. The second aspect is the criticality of application. Like application. Criticality of application. You must have seen the variety of the applications. Like say you are just using the joining to join the steel plates for making the railing or gate or the window. In those cases, if the joint fails, there may not be a threat to the life of the human being. Okay, so there are few non-critical applications. If they, in those conditions, if the joint fail, you don't care, like except the functionality will be lost, but there won't be any threat to the life. There are number of cases where there is a possibility for threat for life, where you have like moderate threat to the life is there in automotive field. You see, you are driving something at 100 or 120 kilometer speed, and suddenly your system gets failed and you are off the road. So there is a certainly, but there under those conditions you may lose your leg, you may lose your hand, but still the threat to the life may be limited. If you talk of the nuclear reactors, if the failure of the nuclear reactors take place where a lot of the variety of the steels are joined, if the joints fail, then certainly there will be disaster, just like Union Carbide in Bhopal. Maybe thousands of the people will be affected and they may lose their life. Similarly, there is aerospace, aerocrafts. So if the aerocraft or the plane, if no large system can be developed without joining, and if the joints fail, especially the structural failures of the joint of the major systems take place, then what will happen? There will be not just the loss of life of say 100, 150, 200, 300 people who are on board, but at the same time the high value asset will also be lost. So the criticality here will depend upon the application. See, so the damage tolerance or the tolerance to the discontinuities should also be linked with the criticality of the application. That is why the fracture toughness based approach for designing a weld joint you may not use for non-critical applications, but certainly the fracture toughness based approach to design a joint must be used for all those cases where there is a life threat to the life and threat to the property at a greater scale. So for critical applications, you must have to assess the tolerance to the damage, and the damage tolerance is compromised somewhat less in case of solid state joining than the fusion joining. Okay, so the damage tolerance is in general good for the solid state joints. I think I have talked a lot about this damage tolerance. Okay, now let me talk a little bit about the sectors where the solid state joining is used and can be used because of the unique features which are associated with. So improved tolerance to the discontinuities, reduced HZ width and related issues So and reduced the residual stress and distortion tendencies. These factors significantly dictate the application of the solid state joining processes in a very high-end applications, say in aeronautic industry. So they will be fabricating the aircrafts, space craft, like ISRO has been using the variety of solid state joining technologies for long to develop the structural components of the spacecrafts. About that I came to know somewhere in 2000 when I met with one of the scientists working there. So similarly nowadays high speed racing cars, uh, they are what you want: good structural strength, good tolerance, reduced weight. So the weld bonding coupled with the solid state joining are extensively used in development of the racing cars, and Honda is one of the example. In literature you can find number of others. So the automotive industry is also, like say, its application is picking up, people are exploring mechanical joining clubbed with the adhesive joining or other solid state joining technologies coupled with the adhesive joining are finding really great applications in this automotive industry. Then, as I said, nuclear industry. In the nuclear industry, you need lot of joining of dissimilar metals. Like carbon steel is usually welded with the austenitic stainless steel. This is one very common. Then martensitic steel, ferritic martensitic steel is welded with the austenitic stainless steel. This is second. And then austenitic stainless steels are also welded with the copper, no, titanium, and the stainless steel ASS is welded in the, like say, in is aeronautical field, that is the different combination. But so these are the different combinations which are very commonly used in the nuclear industry. Likewise, these are also used in the thermal power plants, high temperature systems. In thermal power plants, you will find that some of the components will be working at 200-300 degrees centigrade temperature. Some of the components will be working at 400 to 500, and while others will be working at say 500 plus degrees centigrade. So you need to use the different metal combinations so that you can cut down the cost, as well as you can also develop the systems which can survive for long. Okay, and that is why you need to use the different metals, and whenever the different metals are joined, obviously you will find the issues related with, because they will be heated and cooled. Because of the differential expansion contraction, you will find a lot of problems. Okay, so the solid state joining probably in those cases help a lot. Why? Because on those components I will come again, because in the thermal power plants the approach is altogether different. It is not the weld zone problem, it is the heat vector zone problem, which is mostly common in most of the thermal power plants, and it's called typho cracking. I'll give just one example. You develop a joint, metal is very good. Say one side austenitic stainless steel, another side you have martensitic ferritic steel. Here you have joint. Okay. So what is happening is you can use any good quality material so that weld is good. Most hardly failure will be occurring from the weld in case of fusion. Okay. But if you talk of this side, austenitic stainless steel side or ferritic martensitic stainless steel side. So this side you have the weld decay problem. That is called, like say, the formation of the chromium carbide leading to the corrosion resistance loss. On the other hand, on the martensitic stainless steel side, you will find there is called a typho cracking, which is coupled with the creep fracture after prolonged exposure. This is intergranular fracture, which is promoted especially in the heat effector zone having the fine grain structure. So the problem is of the HZ where you have fine grain structure. So if you see here, and both these are problems linked with the heating, and they are related with the HZ. You cannot do anything with these two problems in case of the steels to be used for developing a joint for thermal power plant application. So for those cases, the efforts are being made, like how to implement the solid state joining. Or develop a joint without much of the heat input so that the properties are not compromised. So this is just an insight of the typical application only. Okay, so let me erase all this. What happened? Okay, so these are some of the applications of power performance I've already talked. Another critical application, or you can say the harsh conditions which are experienced, is like chemical industries. You know, your HCl, H2SO4, HNO3, or very saline environment. So the joints, whenever you make a joint, there is always heterogeneity, metallurgical heterogeneity in the vicinity of the joint. And whenever it is exposed to some kind of the chemical environment, there will always be differential attack, which may be there in the base metal, which may be in HZ or in the weld metal itself. So this differential attack actually causes like galvanic corrosion, pitting corrosion, even general corrosion. So the problems related with the joints is more severe in case of the chemical industries. So you can certainly do using the good filler in case of the fusion joining, but those opportunities are limited in case of the solid state joining. But if the heat input is less, probably the issues related to the HZ will be less even in the chemical industries. Okay, and similar to this is like petrochemical. This is just a subset of your chemical industry. So petrochemical industries also in refineries, where you will say very harsh conditions are existing, joints may not perform because of the heterogeneities. So you see, the joining technology is not just about depositing the metal. You see, in joining technology, what you have to learn is how to develop not just a sound joint. See, all sound joints do not perform well during the real life. The reason being that they may not be technologically sound. What is the meaning? That joint is free from any defect. Okay, but still it doesn't perform. The reason is it has not been developed technologically by considering all possibilities, especially the service conditions, leading to the compromised performance. So what is that compromise in performance caused by? Your HZ is not really favorable, or your weld is not favorable. Although it is sound, but it is not compatible for the service conditions. So that is what we have to understand in these joining technologies. What is needed for a joint to perform for a given service conditions? So the thing that will dictate the development of a good joint which can really perform during the service is the application conditions. So application conditions, there can be many, which can be load, which can be environment, which can be temperature, or so and so forth. These need to be considered while coming up with the joint design and its development for a particular service, so that a joint is able to perform the intended function. Okay, this was about little joining design of the joints. It is not just about like size and shape or throat thickness, but it's like coming up with the technologically sound joints so that it retains its characteristics and doesn't compromise with the properties during the service. Okay. Now I'll talk a little bit about the typical applications of solid state joining. So I don't think it will take long. So I'll just read it out. There are a few applications like structural aircraft section, the blades of the aircraft engines. Okay, the electronic component where basically you feel that it is not the structural joint but electrical connections are to be made. The helicopter rotor parts, the space shuttle fuselage, the exhaust components of the gas turbines, and the aluminum landing gear components. So, likewise, there are number of components which need the solid state joining for effective performance during the service, because your thermal damages, the compromise with the technical soundness of the joint, that will be very negligible. Okay, and that is why they will be performing quite good during the service. Okay, so this was about the applications, and I had shared one file also, a PDF file yesterday. I think I told about that. So now coming to the mechanisms and the roles. Okay. Mechanisms of the solid state joining and the role of the different things like pressure or filler. Okay. So let's talk a little bit about that. So now it is about the conditions or parameters are relevant to the solid state joining. So there are few things which are really mandatory to develop a joint in this case of the solid state joining. What are those? Like in fusion joining, you have to apply heat, okay, so that the fusion of the fixed surfaces can take place, or edges of the plates can take place to develop a joint. Likewise, what are the mandatory things that you feel would be there in case of the solid state joining? Can you tell? Anybody can come up? The things that we have to use in any case for solid state joining, which should be there. Surface, it is important, but this requirement can be neutralized in number of cases. Like say, I'll give example. In friction welding, your surface may be very rough, okay, but in friction welding, what you're doing, you are rubbing the ends with each other to develop the heat enough so that there is a lot of closeness, metallic intimacy, plastic deformation, okay, then you forge. So whatever initially you had, that will be lost, isn't it? Yeah, so this is important in a very limited manner. If it is not there, there are alternatives to deal with this. Yeah, anybody else means any other aspect also? No. My question is little different. You see, like in fusion welding, you have to apply heat, okay, for developing a joint. Similarly, in case of solid state joining, what you have to use in any case, without that there won't be any development. Yeah. Tell me, you see, what is that prerequisite parameter or prerequisite thing that should be there in any case? Without that, they won't be joined. I hope you would have heard. Yeah. So, want to say something? The thing is, if you put the two metallic pieces in metallic contact with each other for 2 years, after some time you will find that they have joined together automatically, even at room temperature, without doing anything. This is what has been experimented. But who has the time of 2 years or 3 months to develop a joint? No, nobody. So the metallic intimacy is one that you need to have. But since you don't like to develop joint on your own because that is not feasible, so what you have to do? You have to accelerate the things. So in all solid state joining processes, the one thing is common in all the cases, that is the deformation, and of course for metallurgical joining there is diffusion. On its own, when just a deformation is happening, probably it is just a mechanical joint. But when deformation is coupled with the diffusion, it is leading to the good metallurgical joint, isn't it? Like you take two wires and twist them each other, then you will get certainly a joint you will get, but that will be totally mechanical interlocking because there is no diffusion across them. So still it will remain the mechanical joint, but when diffusion and deformation both are coupled, you will find a metallurgical joint, which is actually needed for a good strength, a good joint strength. Now these will not, if you take one piece like this, okay, and another piece, this is what I was saying. Put them together, A is placed over A for 2 years, you may after some time you find some kind of joint. Like you must have seen some of the assemblies which were there for like say 2 years, 5 years, 10 years, and after those 10 years if you want to disassemble them, it will require a lot of efforts to make them separate from each other, because so much they come close to each other so much, some kind of the joint is also developed under those conditions. So when you put one component with another, and if at the interface some kind of the diffusion even at the room temperature is taking place, it may take long, that is a different thing, but it can develop a joint which may be weak or strong, that is a different thing. But to develop a joint quickly and of good strength, you need to do something, and there only what you have to apply, mostly it is compressive load. Why compressive? Because whatever your peaks and valleys present both the sides in a component, under the compressive load only you can make them to collapse against each other, so that they form a kind of the interface like this. So in this case what will be there, like the peaks and valleys have got collapsed and they have come very close to each other, so the surfaces would have been rough like this in one side, and another side it may be somewhat lesser rough. But when you apply higher load, these will be collapsing. This is one aspect. When you have the greater RA, say 5 micrometer, or when you have less RA, say 0.5 micrometer, in which case you need the more load to cause the surface layer deformation. Anybody can respond? Anybody can respond? The first one, very good. So if when you have the larger or deeper and higher peaks and valleys, using the somewhat lesser load, you can make them to deform and come close to each other. Okay, but when you have finer one, there is a possibility that they are already very close to each other, isn't it? As compared to the case when they are far away and the local contact is here and there. So in this case, the contact may be just 1% of the apparent area, and here it may be 10% of the apparent area. So in this case, but when you apply, there can be a lot of difference in terms of the temperature conditions. So let's say when you apply a load of say 5 MPa at room temperature RT, nothing will happen. But when the same load is applied of leading to the 5 MPa pressure at 500 MPa, 500 degrees centigrade, the metal will lose its yield strength. All peaks and valleys will be getting collapsed very easily. They will be coming closer. All voids will be broken. Voids will be closed. So the firm metal to metal contact will exist. So the role primarily here is of the pressure is to just bring the two components so close to each other that there is a metallic intimacy. If the two components have come so close to each other that like the contact between them is almost 80%. Like say in all these areas there is a metallic intimacy. Okay. So obviously when it is established, that diffusion across the interface is very stark because of the compositional gradients, the difference in the alloying elements. So the diffusion across the elements, across the interface will be taking place, and that will be leading to the development of the metallurgical bond by the formation of the new grains. Formation of new grains at the interface. So this is good, but prerequisite for atoms to move from one side to another, what is needed? These air pockets must be eliminated. One, because atoms cannot move through air, that's one. And you know, all surfaces will have some kind of, you see, you know, if you see the surface engineering, all the surfaces are made of 4 or 5 layers like this, and in these layers you will find that some of the gases dissolved, then there are oxides and nitrites present, then there is some kind of the deformed layer coming from the machined surfaces, and then undeformed zone like this. There are a number of layers, you know. So atoms will have to cross all these barriers. What is needed? These gases need to be eliminated. One, these oxides and nitrites, if they are there, these need to be eliminated. If there is a rust or impurity or oil or dirt or dust, whatever is present at the surface must be cleaned. Then only your atoms will be able to cross the interface from one side to another. Okay, so that is why what we say, the cleaning is crucial. Now cleaning can be mechanical, use wire brush, use grinding, or use anything that you like. There are many types of the mechanical methods. They can remove the things that are visible to you at the surface. But when it also helps, like chemical cleaning also helps, like use acetone, use alcohol, ethanol or so, or ultrasonic cleaning in ethanol. So that will help to remove all these impurities. So when you have one clean surface, another clean surface, and two are brought in contact with each other, then you have at least, like say, a fair playing field for atoms to move from one side to another, because now there is no air gap, there are no impurities in form of gases, oxides, nitrites or so on and so forth. So this diffusion only will help to form the new grains and develop the metallurgical joint. So I hope now, whether it is the macro deformation or micro, for diffusion to take place, primarily we need the interfacial surface layer deformation. Bulk deformation may not be helping you in any way. I'll tell you an example. Like say this is the component. Right. So if the deformation near the interface of a few micrometers is taking place, like say 5 or 10 micrometer, which is corresponding to the peaks and valleys present at the surface, it's fine. This is typical to your ultrasonic welding or explosion welding, okay. But if the deformation is taking place of the underlying metal, how it is going to help you in joining? No way, because it is not useful in any way. You see, if the base metal is getting deformed or HZ is getting deformed, how it is useful in joining? It's not. The deformation is crucial only to facilitate the interfacial metallic intimacy, so that across the interface diffusion can take place to develop a metallurgical joint. Underlying deformation of underlying metals in both the sides is of no use. So whether you are losing your 10 mm in friction welding or your metal is getting deformed 10 mm in frictionist welding or anything, so that is not helpful, that is not contributing. So the point here is, it may be more crucial to have the controlled micro deformation for joining. This is important. And macro deformation may not be helping. Certainly you are getting your joint, like say in forge welding. What you are doing, you keep on deforming the things so that there is a metallic intimacy and closeness. But you see, the joint is typically being formed primarily due to the interfacial closeness, not due to the deformation in nearby zones. So, like in friction welding, frictionist welding, or even in forge welding, there are a lot of deformation, but the most crucial deformation is the interfacial deformation. Okay, so the cleanliness and the interfacial deformation. Third aspect is the filler. It is surprising to see most of the most of the solid state joining process do not use the filler. That's why mostly say that they are autogeneous. But sometimes it is intentionally used. So when we use the filler and what is the purpose of it? You call it filler, or filler maybe in different forms, like maybe in form of interlayers, which may be of thickness from few micrometer to few millimeters. That is why it may be in form of films or sheets. Okay, so what is the role of filler? Role of filler in fusion joining is completely different than that is used in case of the solid state joining. By the way, what is the role of filler in fusion joining? Coalescence you can achieve even without use of filler. That is what we do in case of, like say, GTAW. Use GTAW for joining two thin sheets. You will have the coalescence without using filler. No, filler is so the filler serves some purpose. So I think I have taught somewhere what is the purpose of physical strength to the. Yeah, this is one purpose. Like say, I'll give you example. Like say your base metal is of like say 300 MPa strength, right? if you use filler of the 100 MPa, your joint strength will be 100 MPa, right? If you use filler of 400 MPa, your joint will be 400 MPa. But in that case, base metals will fail. In first case, weld metal will fail. Okay. So when you use the fusion and the filler kind of thing, you have a choice of altering the weld properties. But that is not the case in case of the solid state joint, because we don't have that luxury, no? In any case, the joint is developed whether you use filler or not in fusion joining. This is one thing. We can certainly get a weld of the desired properties. This is one thing. The second is, like this is very common, like you have a very large area, you cannot have the weld in one pass, so you have to have a groove, and this groove has to be filled in. So sometimes just for filling purpose also this is used, isn't it? So apart from having a weld of the desired characteristics, desired toughness, desired strength, desired corrosion resistance, desired wear resistance, you can choose filler of your choice. But this is one thing. And the second thing, when you are working with the thicker sheets, thicker sections, you have to fill, you have to prepare the edges, and then you have to fill up the gap, isn't it? So the filling is the another purpose that is solved. Okay. Now, in case of SSJ, what is its role? It's different. Even in fusion welding also it is used to deal with the compatibility issues. Compatibility issues like this is A and this is B. So you use C, which is of the intermediate. Say thermal expansion of the A is just 12 units, here it is of 18 units. So let us use it of, say, in between. 15 aega, okay. So use the filler of the 15 units of thermal expansion coefficient, so that the degree of mismatch between the two is minimized. That's the third role. Okay. So yeah, so in case of the solid state, its role is little different. So what is that? Let's say this is the one component and this is the plasma. No, and both are of the high strength. High strength we say 700 MPa. Say just for example 600 MPa. So higher the yield strength, so they will not be deforming easily. So what we can do is, let us put a thin film between the two, which is of the low melting point, low strength, low hardness, and high ductility. So when this thin film is placed between the two and you apply load, the peaks and valleys may remain as it is, but the film will completely fill in the gap. The film will get deformed and fill up the gaps which are there both the sides in form of peaks and valleys. And so the metallic continuity is established through the use of such soft films made of the soft metal. So in case of steel, like say the variety of films are used, copper and nickel films are very common. So they are used. So when they are used, what we get is your metallic intimacy is established. I think here now I should stop, and we'll continue here onwards on the role of the filler.